So, welcome back everybody. We start the afternoon session with a new speaker, Professor Katsura, who will tell us about classification free models and beyond.
Yeah. Thank you for that introduction. And first of all, I'd like to thank Tomasz and other organizers for giving me the opportunity to come here and give a series of lectures. And I'm from University of Tokyo, Japan, and this week I'm going to talk about frustration-free models and beyond. And this is the outline of my lectures. And today I'm going to give introduction to frustration-free systems, and then I'm going to give some way to systematically construct frustration-free models from some known models. And tomorrow I'm going to focus on type chain, both interacting and non-interacting cases, because I think that the aim of this school is more like quantum devices, right? But I'm not really working on quantum devices, but I'm going to try to pretend like quantum device people tomorrow to talk about direct wire, which has a lot to do with quantum devices. But I'm going to focus on frustration-free type chain. And these are mostly on ground state physics, but in the last day I'm going to talk about more dynamics. And quantum mechanical cars are these days quite popular in the dynamics context. And actually we can generalize the notion of frustration-free systems to excited states, like quantum mechanical cars, using the notion of divergence-free conditions. All right, and this is the outline of my entire lectures, but this is the outline of today's lecture. And in the first part, I'm going to introduce the notion of frustration-free systems, but before that, I will talk a little bit about symmetries in physics, and then I will give some preliminary stuff like operator inequalities and spin operators and Anderson bound and so on. And then I will introduce the definition of frustration-free systems. And then in the second part, I will take you through several different examples. But actually, after I prepared my first lecture, I have checked the web page of this summer school, and then I had a look at the lecture by Elio's lectures, and then I realized that most of my examples are already covered by him. So maybe, yeah, but I think this is a kind of a review of his lectures, but probably from different perspectives, so maybe it's good for students. And then in the third part, I will show you some systematic constructions of frustration-free models from known models. All right. So, okay, let me start with something quite general. That's the symmetry in physics. And if you're a physicist, you have been told again and again that symmetries are really important, right? And the reason why they are important is because they lead to the conservation laws, right? For instance, if your system has a rotational symmetry, this means you have a conservation of angular momentum, right? And it's not only conceptually useful, but it's also practically useful because this kind of symmetry allows for analytical treatments of the program. For instance, in a classical Kepler program, you have a rotational symmetry, right? And in quantum physics, for instance, if you consider a hydrogen atom, it has the SO3 rotational symmetry. And if that's the case, then you can reduce the program from a three-dimensional program to a 1D, essentially 1D program, right? And of course, if you're super expert on these programs, they have additional symmetry, right? Their Hamiltonian constructs the Laplace-Runge length vector, so you have additional symmetry. And you can, of course, use it, but at least if you only know rotational symmetry, but you can still reduce the program. So, and this way, symmetries are really useful. But of course, in many cases, in real life, symmetries are often broken, right? And this is an animation that I took from Wikipedia, and people often make fun of us theoretical physicists because we often make a very rough, crude approximation. We are like, let's say this cow is a sphere, but in reality, a cow is a cow. It's not a sphere. Right? So in everyday life, symmetries are often broken, and that's why our, world is quite diverse, right? So we have many diverse phenomena in condensed matter physics. And breaking of symmetry often will result in various phases of matter. For instance, in magnets, the fundamental Hamiltonians often have SO3 symmetry, but in the ground state or in the equilibrium states, it's broken, right? That's why we have uh, ferromagnetism or some other kinds of magnetism, right? Anti-ferromagnetism, spiral order, and so on, right? And in a superconductor, we have a Ur symmetry breaking, meaning you have superconducting order, right? But these days, let's say in the last couple of decades, people gradually became realized that symmetries can also enrich the phases of condensed matter systems. And this is partly because people found the topological insulators around 2005. It's already almost 20 years ago that people found these topological insulators with time-reversal symmetry. And so, yeah, it's too dark, but this is the cover page of physics today, and this is the dispersion duration of the surface state in topological insulators like this selenite. So, yeah, but it's too dark. Okay.
Awesome.
We'll need whiteboard.
I can control it.
So, is that one? No, they go from content.
I see. That's awesome. Yeah, okay. So the one I just and this, yeah, it's not so important actually. So this is just a surface state found by office measurement, and you see you have a direct cone here, right? So and this is a consequence of the topological invariant Z2 topological invariant for topological inference. But in any case, topological insulators are just non-interacting fermion system, electron systems, but later on people found something similar in interacting systems which are called symmetry protected topological phases, and which are beyond the lambda paradigm, right? Because they are not characterized by the symmetry breaking of some order parameters. And okay, but so far I've been talking about the notion of symmetries, but in quantum physics, symmetries can be made more precise because they just mean the presence of conserved quantities charges. And here, by H I mean a Hamiltonian, and A is a Hermitian operator. So, these days, non-Hermitian physics are kind of popular, but in my lectures, I'm entirely focusing on the Hermitian Hamiltonian. So this is Hermitian. And when H and A are commuting, then they can be the other simultaneously, right? So in other words, you can make H in this block the atom form if you write it in a matrix form. And these blocks are labeled by the eigenvalues of this operator A. And this way you can reduce the problem, right? Because originally you have a huge dimensional matrix, but this way you can reduce the dimension of each block. And for instance, coming back to the hydrogen atom Hamiltonian, we have a rotational symmetry, meaning these angular momentum operators are commuting with the Hamiltonian. Of course, some of them are, they are not mutually commuting, so we need to pick one of them. But anyway, for instance, if you pick LZ, then these works are labeled by the eigenvalues of their field. And of course, this is just a particular program, but for instance, if you go to many body physics, there are a class of classes of integrable models for which you have many conserved charges. I mean, if you increase the system size to infinity, you have infinitely many conserved charges. And a typical example is the S equal 1/2 Heisenberg model, which was solved by Bethe in 1931. And I think Thomas should be talking about integrable models next week, right? But yeah, I'm not going to talk about integrable models. But anyway, so this is a typical example of systems with many conserved charges. And because of the presence of these conserved charges, we have a strong constraints on their dynamics, right? Okay, so now let me give you some quiz. And okay, so again, H is a Hamiltonian and A is a Hermitian operator. And as I said, when H and A are commuting, then they are simultaneously diagonalizable, meaning that they have a simultaneous eigenstates. And the question I want to ask now is, does the converse hold? And okay, maybe I can ask you. So, if you think this is yes, maybe you can raise your hands.
What do you mean by converse?
Because I mean, this direction is true, but how about
the
direction? Opposite, yeah. And how about no? If you think no, maybe you can raise your hands. Do you mean that is correct? Yeah, don't be shy.
Could you rephrase the question, please?
You mean this way? I mean, if H and A are commuting, then they have a simultaneous eigenstate.
Yes.
And the question I want to ask you is if the opposite is true, converse is true, the other direction.
No, I mean,
Let's try again.
if it's literal, then no, because if they have n eigenstate, just one, maybe there are other vectors that are not mutual for them.
Yeah, let's just consider the simplest case. Let's just consider one single eigenstate. And they could have many simultaneous eigenstates. But
No, I'm making the point that maybe there is one vector that is an eigenstate for both of them, and then there are vectors that are eigenstate for just one of them, but not both of them. So it's I can construct such metrics explicitly, I guess.
yeah, this is more or less the answer, I think. But anyway, so I mean, okay. So the answer is no. Okay. And the next question I want to ask you is, can you provide a counter example? Yeah. Any simple, just a single particle problem is enough.
Say,
I mean, you can find an example in undergraduate quantum mechanics, which you have everyone as well. So, can you give any example? No? Just,
Could you say more about this or something else?
maybe just a match. Like matches whether we plus yeah, but that's a bit too trivial. Right? You are talking about the identity and the sigma zeta.
Yes.
They can
But can you?
They commute.
Okay, so yeah, let me show you the answers. So
It's 3 by 3 matrix where the Hamiltonian is purely diagonal, and A has the diagonal block 1 by 1 and the off diagonal block 2 by 3.
uh,
Then they have one eigenstate in common and the other are different.
I see. So you are talking about this kind of matrix, right?
Yes, and the
So,
Hamiltonian is just
this has
yes.
I see. Oh, this is a good example. So, okay, yeah, but what I have in mind is a bit more complicated. Actually, it's an infinite dimensional example, but this is the, this wave function of the hydrogen atom, right? And because this is a simultaneous eigenstate of any of these, angular momentum operator, and they're not commuting with each other, right? But nevertheless, they have a simultaneous eigenstate, which is the s orbital wave function. And we have these relations. This psi 00 is a simultaneous eigenstate of all these guys. And also this is an eigenstate of L squared with zero eigenvalue. And this is actually a baby example of frustration-free systems, which you can find in elementary quantum mechanics. But yeah, your example is also fine. Yeah, it's simple. Yeah, I like it. All right. So now let's move on to the crash course in inequalities. Yeah.
When you said frustration-free, what do you exactly meant?
Yeah, that's what I'm going to talk about in the coming slide. So, but before that, let's first introduce the notion of operator inequalities, and let me run through a crash course in inequalities. And okay, so let me first introduce the notion of positive semi-definite operators. And there's a nice appendix in Tasaki's paper about Hubbard model, and he recently wrote a book about quantum anybolic physics in his book. But anyway, so let me introduce what they are. And this calligraphic H is a finite-dimensional Hilbert space, and A and B are Hermitian operators acting on H. But you can just simply think of them as matrices. And here comes the definition. So we write A is greater than or equal to 0 and say A is positive semi-definite, or PST for short, if expectation value of A in any state psi is non-negative. And the second definition is that we write A is greater than or equal to B if A minus B is positive semi-definite. And important lemmas just follow from these definitions. And the first lemma says that A is positive semi-definite if and only if all the eigenvalues of A are non-negative. And the second one is, okay, let's C be an arbitrary matrix on H, then C level C is positive semi-definite. And the corollary follows from this lemma is projection operator P is positive semi-definite. And the final one is if A is positive semi-definite and B is positive semi-definite, then we have A plus B, which is positive semi-definite. And these are simple to prove, but maybe I can use the whiteboard to show the proof. And okay, so lemma 1, so let's find the eigenstate of A. And if we assume A is positive semi-definite, then expectation value of A in any state psi is non-negative, right? Then suppose psi is normalized. Then you have psi A psi equals lambda, but it's by definition non-negative, right? This is the sufficient condition, but you can prove the other way. Okay, because A is a Hermitian operator, so if okay, so this is the spectral decomposition of A, you can always write this way, right? So JJ. And if A is positive semi-definite, then any AJ is non-negative, right? And then, our assumption is this, and AJ is greater than or equal to 0. And then if you sandwich A by psi, you just get this, right? Psi, sorry. Yeah, this is there. And because this is non-negative, this is non-negative, right? And this way, we can prove lemma 1. And lemma 2 is easy to prove because, if you sandwich C by psi, you just get C psi squared, right? So this is non-negative. And because if this P is projection operator, P squared equal P, right? P squared equal P. And because P and P dagger are the same, because P is transition, you have P dagger P. So any projection operator is positive semi-definite. Okay, thank you. And so, okay, let me prove lemma 3. And this is almost obvious, right? So if you sandwich A plus B by psi, then you get psi A psi plus psi A psi. But because both are non-negative, some of them should be non-negative, right? So, yeah, it's very easy. It's okay? Yeah.
On mine, assume that operator is a positive. Finite space.
Yeah, I'm always assuming the finite dimensional system, Hilbert space. So, yeah, of course, if you go to continuous system, it's more subtle. And now, okay, so let me talk a bit about the spin operators because I'm frequently using the properties of spin operators. And so let me start with the spin 1/2 operators, and this is the spin operators for single spin. And by 1, I mean 2 by 2 identity matrix, and sigma x, sigma y, and sigma z are standard power matrices. And by up and down kets, I denote these, two-dimensional vectors, and they are diagonalizing the sigma z operator, the 2 by 2 matrix. And you can express arbitrary state in C2 by linear combinations of up and down kets this way, but you can think of it as just a two-dimensional vector alpha beta living in C2. And you can also define dual branch states this way via row vectors. And then tensor product of, okay, let me introduce the tensor product of vectors. Actually, I always told my students that there are two kinds of people in the world. Those who understand tensor product and those don't. And I think most of you guys understand the tensor product. But just in case, let me introduce the definition of tensor product for the two-dimensional case. And this V1 case is alpha beta, and V2 is this one. And tensor product is like this. So here, in the place of alpha, I put this two-dimensional vector here and there. And if you multiply alpha by V2, you get alpha gamma alpha delta, and here you have beta gamma beta delta. And we often write it as Vn this way because it's annoying to write, this tensor mark again and again. So this is an abbreviation. And now let me introduce the definition of the tensor product of matrices, again based on this 2 by 2 example. And we have here these 2 by 2 matrices, and here is the definition of A tensor B. And again, in the place of little a, I have B here, and like this. And if you multiply small a with B, you have this 2 by 2 block A, G, and AH, and I'm ready to write out all the elements, and you can go on this way. And this way, you can naturally introduce the notion of matrix vector multiplication for this tensor product. And if you multiply A tensor B by B1 tensor B2, then you get this vector on the right? And okay, now let's move on to the case with many spins and spin operators acting on C2 to the n for tensor product of C2. And this is abstract notation, but you can just think of it as the Hilbert space of spin chain made up of n sites. And this is the formal definition of the spin operator acting on site J. And A runs from X, Y, Z. And you see, it's almost like identity, but not quite, because it acts on site J non-trivially like this. But we don't really often write this way. If you are a physicist, you prefer this shortcut notation, right? Shorthand notation. And okay, and let's do the exercise. And okay, let's write down this operator in the form of matrix. So the program I will do is map what this guy looks like in the form of matrix. And in terms of R matrices, it looks like this, right? And literally, this is a tensor product of sigma x and sigma x, and this is the sigma z tensor 1. And if you write them out, they look like this, right? And according to the tensor product group, you have on the top group left and the bottom right corner, you have 0 matrices, but here you have a 0, 1, 1, 0, 0, 1, 1, 0. And this is easier. Oh, sorry, yeah, I made a mistake. So it's 1. So it's easier, right? Because here you have 0, but on the diagonal you have 1, 1, and minus 1. So if you add them up, you have 1, 0, 0, 1. Yeah, and this is answer. So the point is that we can always think of these many spin operators as a matrix. Of course, in practice, if you have many spins, it gets more complicated. It's correct, right? So, okay. I just think. Okay, thank you. Okay. And you can also express the spin space this way, and we often abbreviate these tensor product marks because it's annoying. And so far I've been talking about spin 1/2 operators, but you can also define spin S operators in states, and these are the definition of spin S operators, and spin operators satisfy these commutation directions, and you can also introduce spin raising and lowering operators by this plus minus, and this S square is the spin magnitude square. But it's diagonal. I mean, this is proportional to the identity matrix. And for a single spin S, you have two S plus one dimensional Hilbert space denoted by C to the 2S plus one, which is spanned by these states. I mean, this S cap, it states from minus S to S. I mean, they are eigenstates of SV. And this plus minus, raises or lowers this n, the value of n. And for many spins, you have n for tensor product of C to the 2S plus 1, and this is the definition of spin operators. And they satisfy these commutation durations. And yeah, sorry, there's a typo. They should be n, but anyway, this is the spin state. And so I'm gonna frequently use the addition of spins. And by S total A, I mean the total spin of operators. And this square is, sum of these squares. And for two spins, here are eigenstates of S total square, and this guy is called a spin singlet, and this is an eigenstate of S total square with eigenvalue 0. These are spin triplet states, and their eigenstates of S total square is eigenvalue 2. And for two spin ones, we have three different subspaces, and spin singlet looks like this, and these are spin 1 and spin 2 operators, and they are not normalized. But, you have to have something like square root 3 and so on. Anyway. Okay, now, let's introduce the notion of frustration-free system. But before that, let me tell you a bit about Anderson's paper in the 1950s. And Phil Anderson wrote a lot of papers which are influential in condensed matter physics, but probably this one is not so known, not that famous. But this is a paper in 1951, and in this paper he was discussing the ground state energies of the antiferromagnetic Heisenberg field in arbitrary dimension, and this is the Hamiltonian of the Heisenberg model, right? And interestingly, this paper is literally a half-page paper. And this is a copy of the page, and it's not even one page. Life was easy at that time. Unlike these days, people didn't have to write lengthy papers. But I mean, this paper is quite interesting. So what he was discussing is quite interesting. And around here he got the upper and lower bounds on the ground state energy of Heisenberg antiferromagnet. And here's the result. And the upper bound is quite easy to understand because for antiferromagnet, you can assume the new state, which was also discussed this morning by Elio, right? So then, if you use this state as a variational ground state, then you can get the upper bound this way. And here, N is the number of spins, and Z is the coordination number. For instance, in 3D, Z is 6, right? If you consider cubic letters. But lower bound is not so trivial. You have something like this, right? But in the end, if you take the infinite S limit, the classical spin limit, they go to the same value. So the new state becomes an eigenstate in the classical limit. And okay, now let's prove the Anderson's bound. And here is the setup. And this H is the total Hamiltonian. It's a sum of small hj. And for instance, in this example, this was like a 6-side system, and H1 is acting on these two sides on this one, and in this particular example, you have 6 local Hamiltonians, and each sub-Hamiltonian Hj satisfies this inequality, but this means the lowest eigenvalue of Hj is Ej upper 0. And then you can get a lower bound for this total Hamiltonian. The ground state energy of the total Hamiltonian is lower bounded by the sum of the ground state energies of the sub-Hamiltonians. And here's the proof. The proof is quite simple. So let's phi naught be a ground state of H. Then since phi naught is not necessarily a ground state of small hj, we have this inequality, right? If you sandwich hj by phi naught, you get hj up and down. And now let's apply this inequality to Heisenberg on the ferromagnet. And you can generally write the local Hamiltonian in this fashion. And here, this J is fixed some site, and I, this index I, runs over the nearest neighbor sites. And this is an example for cubic life. And you can rewrite this Hamiltonian in this way. And here, S total squared, this S total means the total spin of these 7 spins, and this is the sum of the spins on the blue dots. And you can rewrite it this way. And then, this S total square obtains the minimum value at when S total is Z minus 1 times S. But this will be maximized when this is ZS. So, yeah, if you plug them in here, then you get this lower bound for the ground state energy of the local Hamiltonian. And this proves the lower bound Anderson obtained in his paper. Okay. Okay. Now let's generalize this idea to more general Hamiltonians. And again, here's the setup. So the total Hamiltonian is made up of this small hj, and each sub-Hamiltonian satisfies this operator inequality. And then here's the definition of frustration-free Hamiltonian. So this Hamiltonian is said to be frustration-free if there exists a state psi such that hj psi is equal to ej upper naught psi for oj. And this is the definition. And you see this state psi saturates Anderson's bound, right? And one thing to know is that this definition really depends on how you decompose the Hamiltonian. You can always say your ground state is an eigenstate of your Hamiltonian. In each case, this J only runs one single index, right? But that's not so useful. So we already need to specify how you decompose the Hamiltonian into local ones. Yeah.
Like HJ, you mean that the Hamiltonian is like block diagonal?
No.
Each HJ is a block. No.
That's really important. Actually, they don't have to commute with each other.
This is just some composition.
Some decomposition.
Okay.
In many cases, we assume the local decomposition, spatially local, but that's not even necessary. But in practice, people often assume that. Yeah.
So EJ naught is precisely the lowest eigenvalue of HJ, or just some constant that limits it from the bottom.
Yeah.
So it's precisely the lowest eigenvalue.
Exactly. Yeah. And questions?
Yes.
Okay. And interestingly, many solvable models, exactly solvable models, fall into this category. And for instance, imagine the Gauche model, a KOT model, and historic model, code model. They all fall into this category. And I think many of them are covered by Elio's lecture, right? Anyway, so, but in the coming few slides, let me give you these, famous examples. So So let me start with the simplest case, which is the ferromagnetic Heisenberg model in one dimension, and then I'm going to introduce the magenta-Gauche model. And okay, so this is the Hamiltonian of the ferromagnetic Heisenberg model in 1D, and for simplicity, let's consider S equal 1/2, and this J is positive, but you see you have a minus here, so it's a ferromagnetic model. And for some reason, I have shifted the energy origin by adding a constant here. And I have imposed periodic boundary condition, meaning Sn plus 1 is identified with S1. And this model has S2 symmetry, meaning that Hamiltonian commutes with each component of S total. And yeah, this is the definition of S total. And you can rewrite this local Hamiltonian in this fashion. So this is the 1 minus 1/2 times total spin squared. And here you have a total spin, right? So, and this is actually proportional to a projection operator because you can rewrite Hj in this way. This is the more precise way to define Hj. And this Jp s equals 0 acts on the sides j and j plus 1. And this p is a projection to a singular state. And this sign is a spin singular state, which I have shown earlier, right? And this is, because this is a projection operator, it's positive semi-definite, and because some of the positive semi-definite operators is positive semi-definite as well, so you have this inequality. And you can show that this is frustration-free because all up state is annihilated by any of the states j, because if you act this sign on any pair of neighboring spins, you always get 0, right? Because up is orthogonal to sign. Anyway. So this is a zero energy state of the total Hamiltonian. And you can also write the other ground state by acting with the spin lowering operators again and again. Because you have a SU2 symmetry, they are also ground state of the model. And you can prove that each ground state is unique in each total SZ sector using the stuff like Perron-Frobenius theorem. And yeah, and this is an exercise for you, but you can extend this kind of model to higher spins and to any dimension. Or you can say arbitrary graph. Okay. So now let's now introduce the magenta-Gauche model. And this is a spin model for, spin 1/2 model in one dimension. But this is not a ferromagnetic model. It's not like an anti-ferromagnetic model. And this is the definition of the local Hamiltonian. And you see, from this you have interaction between the neighboring states, and from here you have a nearest neighbor interaction. And this model was considered by Magenta and Gauche here. And actually, I had a chance to visit Kolkata 2 years ago, and I was visiting the SM Bose Institute there. And that institute was invented by Magenta, this Indian guy. So anyway, and here I assume n to be even number, even integer, and I impose the periodic boundary conditions. And again, this model has sp2 symmetry, meaning the total spin operators commute with the Hamiltonian. And you can rewrite this local Hamiltonian in this way. And you see, again, you have a total spin operator for these three spins. And so actually you can prove that this is proportional to a projection operator. Because you can consider the addition of 3 spin 1/2, and you have either 1/2 or 3/2, right? And if this is 1/2, then you get 0. But if this is 3/2, you have no 0 value from here. So this is proportional to the projection to in 3 halves. So this will project out in 1 half. So now let's write down the ground state of this model and prove that this is frustration free. And okay, so this green overall means dimer state. So it's just a spin singlet state. And this is one of the ground states of the model. So this is you see just a product of spin singlet states. And graphically, you can think of it this way, right? And the other one can be obtained by shifting the system by one side translation, and then you get the other states. And they are not orthogonal to each other, but in the infinite size limit, they are orthogonal. And remember this Hj is proportional to projection to total spin 3 halves on each triangle. But since the addition of the spin singlet here and the spin 1 half stays here is, just 1 half. So you never get spin 3 halves from any of the triangles. So if you act with local Hamiltonian Hj on either this guy or the other guy, you always get 0. So this way you can prove that the Hamiltonian is frustration free and you have this explicit ground state. And it's a bit non-trivial to show that there are no other ground states, but these guys proved that in the 80s. And you can also consider higher dimensional generalizations of magenta-Gauche model, and you can also study the higher spin version, which was studied by the group of Frederick Miller. Okay, now let's move on to the KLT model. Okay, yeah.
Just a question. Is there some kind of physical way of thinking about frustration-free model? I mean, like we defined it in some rather mathematical way, let's say, but how can we think about it? What gives us? I mean, of course we can check formally, but what next? How to think about that?
So yeah, I think I'm going to talk about it in the coming slides, but I agree. So the models are rather artificial, but maybe you can think of them as a kind of a fixed point models. I mean, in some cases, even if you are a bit away from those special points, some of the physical properties remain unchanged, like topological properties, for instance. So, in the context of DMRG or tensor networks, people consider the tensor network minimization group, right? In that context, this kind of a special space more like a fixed point in the tensor network minimization group.
Okay, but what kind of, as you said, physical quantities, right? But what kind of physical quantities should I think when I hear the phrase frustration-free model?
Yeah, it depends. I mean, if you consider the stuff like a correlation function, it's quite sensitive to the difference of the models, right?
Mm-hmm.
For instance, I'm not sure if the Elio was talking about the topological index for the Holden phase. He was talking about this Zunido-like terms, right? But anyway, so you can define a topological index that can distinguish between the topological and trivial phases. And for instance, this kind of index, because this is index, this is robust against a small correlation. Right? And for such a quantity, you can prove that this index at the frustration free point and the same index of the frustration free point are the same. As long as you don't cross the gap between them, energy gap.
Okay, thank you.
And this is what more I'm going to talk about for the KLT model, but anyway, so let me explain what it is. And okay, so let me start with the Holden projection. And this is about the conjecture about spinless Heisenberg antiferromagnetic chain. And this is a schematic picture of the Heisenberg chain in one dimension, and they are interacting. The neighboring spins are interacting by this Hamiltonian, and this J is positive, so it's antiferromagnetic. And the conjecture is the following. I think that this morning Elliot was talking about almost the same thing. For spin, half of the integer spin, you have a gapless phase in which the spin-spin correlation function decay with power law. And the spin 1/2 case is solvable by the Bethe ansatz. But for integer spins, you have strikingly different properties. First, the ground state is unique, and there is a non-zero spectral gap above the ground state, which is called the Holden gap. And unlike this former case, the spin-spin correlation function decay exponentially with distance. And this was established in many different ways. For instance, experimentally found a lot of examples of Holden gap systems in organic spin chains and inorganic spin chains and so on. And theoretically, people used to verify this conjecture using the exact diagonalization and quantum Monte Carlo and so on. And this is the partial reason why Holden was awarded the Nobel Prize in Physics in 2016. And for instance, this Shinji Todo is my colleague at the same department, Tokyo University, and he's an expert in quantum Monte Carlo, and he computed the accurate values of the Holden gap for S equal 1 to 3 using the quantum Monte Carlo, and these are the values. And you see for S equals 3, the gap is quite small. So it's almost gapless.
And it's in units of G, right?
So yeah, so here I said J1. Yeah, thank you. And so, so unfortunately, this Heisenberg model itself is not solvable, it's not frustration-free. But Affleck and others came up with a model, LKT model, which looks a lot like the Heisenberg model, but is frustration-free. And this is the Heisenberg interaction, which is also called the bilinear interaction. This is some additional term called the biquadratic interaction. And again, I have imposed the periodic boundary conditions, and this model has basic symmetry. And you can rewrite this Hj this way. So I have added this constraint so that this is proportional to a projection operator. So here it's a projection to spin 2 for these two spins. And you see here we have a total spin here and there, right? And if you fuse two spin 1s, then you get total spin 0, 1, or 2. And if this is 0, then you get 0. And if this is 1, from the second term you get 0. But if this is 2, then you get something non-zero. So this is a projection to spin 2. So it project out the spin total spin 0 and 1 state. And now let's prove that the model is frustration free. And here, by this spin single state, and by this gray oval, I mean a projection to spin 1 space. And here is a pictorial representation of the ground state. So the construction goes as follows. So you first arrange these dimer states in this one-dimensional fashion, and then you project the head and tails of these dimers down to in one subspace by this gray oval, and then you can show that each projector annihilates this state. This is because if you look at these two sides, you already have a spin singlet here, right? And if you add a spin singlet and these two spin 1/2, you can only get a total spin 0 or 1 state, but you never get a total spin 2 state. So if you act with the Hj on this state, then you always get 0. So this is a zero energy state of the ground state. And for this state, AKLT proved that the ground state is unique, and there is a zero energy gap above the ground state, and the spin-spin correlation function decays exponentially with distance. So so this model provides a partial support of Bourdain conjecture, although the model itself is different. And so, yeah, maybe some of you are not so happy with this graphical representation because it's a little bit sloppy. So maybe let me write down the ground state inequation. And okay, so this is the singular state inequation, and you can write it this way. So this is a scalar, but you can think of it as a product of a row vector and a column vector this way, and this is a scalar product, a scalar quantity, right? And now consider the product of two singular states, and then you have this. But here you have a product of the column vector and the row vector, and if you multiply them out, then you get 2 by 2 matrix this way, right? So, but I mean, these elements are not in one subspace, so you have to project them down to the spin 1 subspace, and here is the projection to spin 1. So this P upper 1 projects up to plus, and if you act with P1 on up down or down up, you get this 0 k over square root 2, and if you act with P1 on down down, you get minus k. So this way, you can project these states down to the spin 1 subspace. So let's do this. So, if you act with this P1, here you get this 2 by 2 matrix whose elements are in one subspace. And you can continue doing this, product and projection again and again. And then you get a matrix product expression for the AKLT state. And yeah, so here, this A upper J means these 2 by 2 states, right? And you can generalize this kind of notion to arbitrary dimension of the Hilbert space. You can consider higher spin generalizations of the AKLT model. And these more mathematical people have found the notion of finitely correlated states in the early 90s. But this is just a generalization of this kind of matrix product states. And now let me come back to his question earlier. So the frustration-free model is just a fine-tuned single point, but you can think of it as a representative of some phase. And so that's located in a more general Hamiltonian. So this is the Hamiltonian of a bilinear biquadratic Hamiltonian for spin 1. And you have a bilinear term with cosine theta here and a biquadratic term with sine theta here. And the phase diagram, the model is not solvable in general, but the people numerically study the phase diagram quite extensively by Hosho and others. And then if you vary the parameter theta, you get 4 different phases. And in this column, spin quadrupolar phase, you have a gapless ground state, and you have a dominant nematic correlation. And this ferromagnetic phase is just a ferromagnetic phase. And in this diagonal phase, you have 2 ground states, but above them you have a finite vanishing spectral gap. And in this region, we have a golden phase characterized by the gapped unique ground state. So unlike the diagonal phase, we only have a single ground state. But if you impose open boundary conditions, you have degenerate ground states, which are related to the edge states. And in this phase, you don't have a conventional spin order. It's not antiferromagnetic at all, but you have a hidden antiferromagnetic order characterized by the non-local strong string order parameter. And you see, Heisenberg model is here, but the KT is a bit away from here, but still there in the same phase. And as I said, this model, Heisenberg model, is not solvable, but they share similar properties. So, I mean, for instance, the correlation functions are different, but you know, in any case, for instance, the spin correlation function in most models just go to zero.
Oh, you mean this Haldane? Sorry, you mean this Haldane? Heisenberg was Haldane? Or
No. I mean, this is just a single point in this phase.
yes. Yes. So, like, let me rephrase. Did I understood correctly that okay, frustration-free system is like some specific point presented in this class, and we're interested in them because they're like more easily solvable.
Yeah, this is just like a hydrogen atom in elementary quantum mechanics. Right? I mean, it's a textbook example which is, you can solve by hand.
Okay.
So you can learn a lot, but in reality, the system is more complicated.
Okay, so if I think about, if I hear frustration-free system, I think about like analytical solution.
Yeah.
Okay, thank you.
So yeah, this is more or less the conclusion here. So that this AKT model is prototype representative of this SPT holding phase, and from which you can learn a lot about the physical properties of the holding phase. And I'm not sure if I have time to. I think you have learned a lot about the SPT phases in various lectures, right? So let me, run through it very quickly. So, I mean, if you don't impose any symmetry to the Hamiltonian, you have many different parameters. And for instance, in this two-dimensional example, you have two parameters, lambda 1 and lambda 2, and this origin corresponds to the quantum critical point at which it's gapless. But if this is the case, you can go from any point in the phase to any other point without closing the gap, right? But if you impose some symmetry, in some cases, you are not allowed to have non-zero lambda 2. So you are confined to this one-dimensional parameter space. And if this is the case, here you cannot go from the left to the right without crossing the gapless point. And in which case you have two different phases. I mean, for this example, you have this VT on the left and the trivial on the right, but which is trivial is not so important here. And in any case, we have two distinct phases. And so, I mean, for the notion of SPT to be meaningful, you need to impose certain symmetries. And that's really true for the Holden phase, because, I mean, if you don't impose any symmetries, the Holden phase doesn't make any sense. So you need to impose some symmetries. And actually, this is, phase is protected by any one of these symmetries. C2 cross C2, or time reversal, or bond-centered inversion. And this Z2 cross Z2 is generated by these 3 pi rotations, and this x pi is a pi rotation about x-axis, and this is about y-axis, and this z pi is a pi rotation about z-axis. And they are not totally independent, but this group is isomorphic to this guy. Okay, so far I've been talking about the 1D examples, but let's move on to higher dimensional examples. So let me discuss Kitaev's toric code in 2 dimensions. And I think you also learned a lot about the toric code, right? Okay, but so anyway, so let me review it from my perspective. And the model is defined in 2D square lines, and I impose periodic boundary conditions in x and y directions. And in this model, spin 1/2s are living on edges, not vertices. And by n, I mean the number of vertices, not I mean the number of edges is 2n in this case. And here's the Hamiltonian of the toric code. So you have two terms. The first term is often called the electric term, and the second one is called the magnetic term. And in the electric term, you have vertex operators. There's a V, and this guy acts on these four spins around this vertex. That's why it's called vertex operator. And this for get operator, which I denote by VP, looks like this. So this guy acts on these four edge spins. But here we have a sigma x. This is the product of sigma x. And the important point here is that they are all commuting. And you know, if V and BP are far apart, if they don't touch, it's obvious that they are commuting. But what is non-trigger is when they are touching like this. Right? But even in this case, they share two base spins, right? And because the power matrices sigma z and sigma x are anti-commuting, these are commuting, right? Because you anti-commute this guy twice. So in any case, these operators are all commuting. And now let's prove that this toric code model is frustration-free. And so let's discuss the properties of local Hamiltonians. So you see AV and BP are made up of these Pauli operators, so they square to 1. That means their eigenvalues are either +1 or -1. So from this you can easily get the Anderson bound, right? So because you have n vertices, the lower bound for the ground state energy is -n multiplied by Je plus Jm. And so now let's look for the ground state. And you can see that this O up state is a ground state of AV because AV is diagonal in signal C, right? So if you add this minus AV on this state, then you get just a -1. So this is a ground state of O minus AV, but this is not even an eigenstate of minus BP. But now let's consider this state psi. It's defined like this. And this is a non-zero state. You can prove this by, I'm going to show you later. Anyway, so it has a nice graphical expression in terms of loop configuration, from which you can convince yourself that this is a non-zero state. And since AV and BP are commuting, you can take minus AV all the way to the right. And because minus AV all up is minus all up, so you have this iteration. So this is actually a ground state of each minus AV. And since this is this holds, and all the B operators are commuting with each other, you can show that this is a ground state of each minus BP. So this way, you can show that this state psi saturates Anderson's bound. So this is a ground state of the model. So now let's introduce a nice graphical representation of the state psi. So you can identify this up spin is an empty line and the down spin is field line. And then, if you add this, this state is just the up state around this square. And if you add with EP on this state, you get this loop around this pocket P. And if you have this, then you flip the empty and field lines like this. And yeah, this way you can convince yourself that each loop configuration has a corresponding spin configuration and vice versa. And this is a graphical expression for the state side. So it's a equal weight superposition of this loop configuration. More precisely, in each configuration, uh, there are 0, 2, or 4 lines emanating from each vertex. And the state side, which I showed you in the previous page, is an equal weight superposition of all such loop configurations. And actually, the same diagram appeared in the high temperature expansion of the classical IC model, which I'm going to discuss tomorrow. And yeah, I don't have not much time to talk about this one, but you can also think of this state as a projection of cluster state down to this physical subspace. And now let's discuss the topological degeneracy in this model. And actually the state size is just one ground state, but you have other ground states. We actually have 4 ground states if you define a model on a torus like this. And you can embed your lattice on this torus, and this is the lattice embedding. And you have a closed paths, Lx in this direction and Ly in this direction. And for each path, you can define these x operators. So alpha is either x or y, but this is a product of sigma x along this path or this path. And this guy commutes with the other element. And because there are only sigma x operators involved in x, it's clear that this x commutes with any of BP, right? But you can also show that any AV commutes with x sub alpha because they always share even number of spins. For instance, if you have AV here, this guy and this line operator share 2 spins here, and for the vertical path, they share 2 spins like this. So they are commuting with each other. So by acting with these commuting operators on one of the ground states side, you can generate other ground states. And these are 4 ground states: psi x x, psi x y psi, and x y psi. And they also have other guys also have nice graphical expression. For instance, this is the graphical expression for x y psi. If you act with the empty state, if you act with x y on the empty state, you have this vertical line here, and you also have other. You can generate other loop configurations by acting with this electric path operator. And this 4-4 degeneracy is robust against local perturbation. And you can also prove that these 4 states are orthogonal, which I leave you to some exercise. I mean, you need to find some other operators to prove that they are orthogonal. Right. And now let's discuss that this size tensor network state. Actually, this is a particular example of a Brooks-Keverson state. And here is a definition of RK state, and RK state is an equal weight superposition of classical configuration, often with constraints. And this was probably first considered by Steve Keverson and Roxer in the context of quantum dynamo model in the late 80s. And this kind of K-state can be expressed as a tensor network. And the psi, the ground state of a toric core, is an example of an K-state. And here's the building blocks of tensor network, and around each vertex you can introduce these 8 local tensor elements, and by connecting these local tensors in a consistent way, you can generate the ground state psi. And you can also make it anisotropic, and it's called a quantum peg vortex model, which was studied on Eddie Aldone and others in this paper. So, any questions so far? Okay, so now let's move on to the final part. So I'm going to discuss the systematic construction of models. And so, I mean, the question I want to address now is if you can make a new frustration-free model from a known existing frustration-free model. And of course, if you do unitary transformation for a given model, you can generate infinitely many uh, new models, but I'm not sure if you can say it's new because they are physically rather equivalent. So, but you can actually generate unitarily in equivalent models using Witten's conjugation, and that's what I want to discuss in the rest of my talk. But let me start with a trivial example, and this is the trivial example of a translation-free model, and it's just a paramagnetic model. You just have independent spins at each side, and this is positive semi-definite because sigma x takes eigenvalues 1 or minus 1. So it's positive semi-definite, and you see this is a ground state of the model. And I mean, this plus minus get diagonalize the sigma x. And you see, this is just a product state, so there is no entanglement. But from this model, you can generate a cluster model by some non-trivial unitary transformation. And this is the definition of the cluster model. And this is sum of this 1 minus sigma x sigma. Sorry, there is a typo. I think this should be z. Sorry. But anyway, this Hamiltonian is unitarily equivalent to this trivial model, and you can write it this way. And the desired unitary transformation looks like this, and this CZ is a control Z. So if you add this CZ on this state, and then you get a non-trivial sign only when A and B are both plus 1. And using this unitary transformation, you can create this trivial model and cluster model. So, and because of this non-trivial unitary, the ground state of the new model is entangled. So, but in any case, so they are rather equivalent because they are created by unitary transformation. The question I want to ask now is if we can do anything beyond unitary transformation. And actually the answer is yes, and you can actually use Witten's conjugation. And this Witten's conjugation was originally discussed in the context of supersymmetry quantum mechanics. And so let me go through what it is. And here's the algebra of n equals 2 supersymmetric quantum mechanics. So you have supercharges Q and Q dagger, both squared to 0. So they are nilpotent. And this minus 1 to the f means the fermionic parity operator. It anti-commutes with either Q or Q dagger. And in terms of these Q and Q dagger, Hamiltonian looks like this. So Hamiltonian is the sum of Q dagger plus Q dagger Q. And because of this, this Hamiltonian commutes with Q dagger and minus 1 to the f. And this simple algebra tells us a lot about the spectrum of the Hamiltonian. So first, any eigenenergy is non-negative because this is positive semi-definite. So here's a schematic picture of the energy spectrum. So all them are non-negative, and positive energy states come in pairs because of this symmetry, psi and theta psi are degenerate, and eigenenergy is zero if and only if a state is a SUSY singlet. By SUSY singlet, I mean a state annihilated by both Q and Q dagger at the same time. And this is just a terminology, but if the ground state energy is exactly zero, then we say the supersymmetry is unbroken. But the ground state energy is positive, then we say SUSY is broken. And I think I can skip it because I'm running out of the time. So I mean, this is two trigger example. If you consider this combination of boson and fermion operators, and if you define this supercharge, then the supersymmetric Hamiltonian is just the total number of bosons and fermions, and for which the supersymmetry is unbroken because the vacuum state is zero energy state of this Hamiltonian. So you have a zero energy state here. And this is a kind of mathematical sophistication that you can prove that the zero energy states are in one-to-one correspondence with the non-trivial cohomology classes of Q. And this is the proof. So any zero energy state psi of the Hamiltonian is annihilated by Q and Q dagger, but this psi cannot be written as a something like Q multiplied by something phi, because this would imply this normalization is zero. This is true, right? I mean, this psi gura is just phi Q dagger, and this psi is here. And because our assumption is that psi is a ground state of the Hamiltonian, so this should be zero. So then you get this is zero, but it's contradicting because we assume that this psi is a non-trivial, non-zero state. So this way, you can prove that zero energy states are in one-to-one correspondence with the non-trivial cohomology classes of Q. Anyway, this is just an abstract way to write it. But what is important here is that we can introduce the way to compute these cohomology classes. And here is the idea. So this M is some invertible operator. This can be anything as long as M is invertible. And then by M, you can consider the conjugation of the supercharge. This Q tilde is MQM inverse. And by this new supercharge, you can define a new Hamiltonian H cubed. And for this new Hamiltonian, you can, for this new supercharge, you can prove this. But in any case, physically, this just means the number of the ground states in the new Hamiltonian is the same as the number of the ground states in the original one. And this is the idea of Witten's conjugation. But I have to admit that this kind of cohomology is a bit too abstract. But you don't have to worry about it. Actually, I'm going to talk about something simpler. I mean, if you consider the frustration-free models, things are simpler. And so let me now introduce the conjugation of the frustration-free model. And okay, let me start with a universal form of a frustration-free Hamiltonian. So you can always set the ground state energy to zero by adding or subtracting the ground state energy. And this is the universal form of the Hamiltonian. It's the sum of L double L. And a zero energy ground state is a state such that Lj psi is zero for any j. And okay, so here's the recipe for the construction of a new model. So by considering the conjugation of L by M, you can define new L operators. And here's your new Hamiltonian H cubed, which is the sum of L cubed dagger L cubed. And you can write down the ground state for this model because this side cube is a new ground state because you have a cancellation between M inverse here and M here. So and because Lj a narrow side, this is a zero energy ground state of the new Hamiltonian. And unlike the previous example, like cluster model, this Hamiltonian is n equivalent to the original one unless n is unitary. And nevertheless, this new Hamiltonian and the original one have the same number of ground states. And actually, in classical stochastic processes, a similar idea was found. I'm not familiar with the classical stuff, but I think sometimes people discuss this kind of transform. All right, and you can slightly generalize the idea. Actually, you can sandwich something positive definite between LJ2 dagger and LJ2. And this Cj is positive definite, meaning that any eigenvalue of Cj is strictly positive. And this doesn't change the ground state manifold. And okay, so here's the definition of a newer Hamiltonian. So you are now sandwiching this guy between LJ2 dagger and the LJ2. But this doesn't change the ground state manifold. So the zero energy ground state again M psi. This is a ground state of this new Hamiltonian. And here is a theorem, but basically this just means the number of ground state doesn't change by this kind of procedure. And proof is a bit complicated, but if you are interested, you can go to my paper. And I think I still have 2 minutes, so let me give you some exercise. So, earlier I have discussed the deformed Majanda-Gauss model, right? And as I said, the model has sp2 spin symmetry, but you can make it anisotropic by introducing the coefficient Ja, and I mean they can be distinct. And so this model breaks the sp2 symmetry, but still you can show that this is frustration free. And yeah, this is a quiz for you. So, and the hint is you can decompose this state J further using some of the positive semi-definite operators. And you can, here I assume that all these coefficients are positive, but you can make some of them negative, but still the model is frustration free. And yeah, if you're interested, you can have a look at these recent papers where they discuss more complicated situations. Okay, so it's almost the time, so let me summarize my first lecture. So I have introduced the notion of frustration-free systems, and here's the Hamiltonian, here's the definition of the frustration-free Hamiltonian. And so the important point here is that these local Hamiltonians do not have to commute with each other. So let's remember the baby example, the hydrogen atom, S-wave function for the hydrogen atoms. You can, in some cases, you can find a simultaneous eigenstates of non-commuting operators. And in the last part of my talk, I have discussed the construction of frustration-free models using Witten's conjugation and the sandwiching method, and they are summarized this way. So for a given model, you can construct a new model which is not unitarily equivalent to the original one. And this way, you can reproduce many known examples of frustration-free Hamiltonians, and you can also construct new models. And tomorrow, I will discuss some of the new examples, like the interacting interactions. So, thank you for your attention.
Yeah. That we can take. So, by proving that it's frustration